For electrical measurements, oftentimes an amplifier is necessary, either to boost the signal from a transducer or to change the output impedance. What's meant by output impedance? Well, here's a picture of an amplifier, and you can see the input impedance and the output impedance. And if we have a high input impedance, then the input voltage won't change really. So if there's a low input impedance, there'll be appreciable current going through here, and we will have a different voltage drop across the input terminals than we would otherwise. So high input impedance acts like an open circuit, and low output impedance would mean that there would be a negligible voltage drop across the output impedance. So VO would be what we would expect. Some transducers have a high output impedance, and we want to change that so we could use an amplifier to rectify that problem. But the most common use is for boosting the signal. So here we see the source and the load connected to the amplifier, where the input voltage comes from the source and output voltage is seen by a load. And what we want is for the output voltage to be the product of the amplifier gain, A, and the input voltage. Well, really the source voltage. But these impedances here will change that. And those are loading effects. What the amplifier actually sees is this ratio, Zi over Zi plus Zs times Vs. So you can see if we have a high output impedance on our transducer, say, on our source, then Vs is going to be a lot smaller, Vi is going to be a lot smaller than Vs. But if the amplifier has a really big input impedance, then that will negate the effect of the high output impedance from the source. You can just see here the effects of the loading on the desired behavior for this system. When we have these non-ideal systems where they have impedances that aren't what we would hope, then the voltages aren't what we would expect. And by ideal, that means that the input impedance is infinite and the output impedance is 0. And amplifiers also have non-ideal frequency response. We would like it if the amplitude or the gain was identical no matter what the input frequency. But the impedances in the amplifier are complex, and so they affect the gain at different frequencies. For example, the wire would have some inductance, and we get this for our transfer function, and we end up with a cutoff frequency beyond which the gain or the amplification starts to decrease. We could also add some capacitance, and then we come up with a high-pass filter. So you can see here the cutoff frequencies that result from having complex impedances. Ideal amplifiers follow these assumptions. These assumptions say that the input into the impedance is 0. That's because we assume that there's an infinite impedance. So 0 current. There's 0 output impedance, so that means that the voltage is just the gain times the input voltage. The output voltage, I mean, is the gain times input voltage. Like I said, the gain magnitude is independent of frequency, and phase shift is either 0 or linear. Infinite common mode rejection ratio, which refers to these amplifiers being used as differential amplifiers. And we'll spend the rest of our time talking about operational amplifiers, which are often used as differential amplifiers. And these have one more assumption for an ideal op-amp, and that is that there's infinite gain. So A is infinite. Here's a circuit for an op-amp, and it doesn't reach all of those assumptions. So it has non-infinite gain, it has some input current, etc. And this can be improved upon. It can reach, become closer to the ideal op-amp with additions to the circuitry. So here's the circuit for a common op-amp, the 741. And it has gain of about 200,000 input impedance of about 2 mega ohms and output impedance of about 75 ohms. So you saw that the gain, the open loop gain, is 200,000 for the 741 op amp. That is too high to be useful. So really small changes in the input voltage would saturate the output. And also, so we use negative feedback so that the input voltages are smaller, and so that the gain is reduced. So whenever we add feedback, we're going to change the gain of this system. So our open loop gain was one thing, but now we have a closed loop system, so we'll have a new gain. And doing this can also improve the bandwidth of the op amp. Bandwidth meaning the frequency beyond which the gain starts to decrease. When we add feedback, then we get a higher frequency. So what we want to do is find the gain for this system, so once we add feedback. And this analysis is based on two assumptions for the op amp. That is, first of all, that there is no current going into the terminals because we have an infinite impedance. And the other assumption is that voltage at this terminal is equal to voltage at this terminal. When we apply those assumptions and use the principle of superposition, we get that the gain for the closed loop system is 1 plus the ratio of RF and R1. So RF and R1, these resistances used in the feedback. And different gain can be used for a different amplification, and then a different gain will also affect the bandwidth of the op amp. So depending on what we want for those parameters, we can choose this ratio here. Here is a block diagram for the op amp with negative feedback. And we want to find out what this gain K is, so the feedback gain. And it turns out that the feedback gain K is 1 over AF. So it's 1 over 1 plus the ratio RF to R1. The smallest gain that this configuration of the op amp can have is 1. Here's a different configuration called the inverting amplifier, and this is the most common configuration for an op amp. And this can have a gain of less than 1. So here we have, here we have the inverting amplifier. So now the positive input, or the non-inverting input, is connected to ground, and our signal with the voltage divider is connected to the negative input. And the same analysis, based on the principle that there's no current flowing into the terminal and the voltage at the terminals is identical, yields that the gain for the inverting amplifier is negative RF over R1. So with this case, we can have gains less than 1. And a range of gains is good for different applications and for adjusting the bandwidth, etc. For a non-ideal amplifier, there is going to be some current going into the terminals, and so we can add this resistance here to balance that bias current that would give us a non-zero output for a zero input. So if we add this resistance here, then we can reduce that bias. Another common use for an op amp is just to change the output impedance of a transducer or of a source. So if we have a source with a high output impedance, but in order to avoid loading effects we want a low output impedance, we could connect it to an op amp just configured as a voltage follower. And that voltage follower will output the same voltage as our source, but we will have a much lower output impedance by doing so.